Thank you so much for joining this session today. My name is Farzaneh Gotz. I'm an AI transformation lead as part of IBM, and I'm your MC today for this chat with Pieter. Oh, sorry, and I repeated that, and I again made a mistake. So today we have Pieter Luitjens. He's going to talk about deploying transformers at a scale. Pieter is the CTO of Private AI, and he's a co-founder and CTO of Private AI. He has worked on software for Mercedes-Benz and developed the first deep learning algorithms for traffic sign recognition, deployed in cars made by one of the most prestigious car manufacturers in the world. He has over 10 years of engineering experience with code deployed in multi-billion-dollar industrial projects. Pieter specializes in ML edge deployment and model optimization for resource-constrained environments. Very excited to have you here, Pieter, and looking forward to hearing about deploying transformers at a scale. Over to you.
Thanks, Farzaneh. Really excited to be talking here today. So, today, I guess what I'm going to be talking about is just deploying transformers at scale and the basically the journey we've been on for the last 2 years in terms of doing that. So the genesis of this talk was, it's come to my attention quite recently that ML ops resources are very hard to find. And as a result, many companies are racking up some pretty large cloud bills. And this really comes from a number of factors, in my opinion. But I guess, like deployment often seems to fall between the machine learning team and the DevOps team. So it can sometimes be a bit of a no man's land. And, it's 2021 now. Deploying neural networks into production is literally 1,000 times easier than what it was in 2016 or 2017. However, it can still seem, I think, a bit daunting from the outside. There's a bunch of different solutions available today. And in particular, it's quite hard to choose which one because there's not many benchmarks comparing the different offerings. And we also found that there's not very many user experiences to learn from. So it's kind of hard to figure out, what should you be really using, what's reliable, what is, maybe not production ready just yet. That was really quite hard for us, and we actually ended up trying a whole bunch of different solutions before settling on the tool stack that we have today. And that's basically what you'll get out of this talk is just the learnings from our experience over the last 2 years, and basically what, in our opinion, the best stack is. I will back this up with benchmarks, comparing some of what some of these systems do. And I think with a few simple things that I'll present today, you should be able to unlock a 10x reduction in your cloud bill when it comes to transformer model serving. In terms of the structure of this talk, I'll be starting off with just what the use case for private AI is and the deployment requirements for us. They will be quite different to quite a few of you, I expect, given that we primarily deploy in our customer compute environment. We don't really do much in our own cloud. And I'll walk through some of the steps that we've taken to get performance up. Great. So on that note about private AI, basically we develop software that redacts text and generates synthetic PI to a very high level of accuracy. You can see for an example, on the right, there's an example of what our system does. And fast, reliable redaction is very important when you're training transformer models due to the memorization ability of transformer models. And transformers are amazing at many things, and this we've been able to build a very high performing system on top of these networks. Apologies. And just a disclaimer that a lot of the software I'll be recommending today is primarily developed by Microsoft. We're also backed by M12, which is Microsoft's VC arm, but I remain impartial in this, and this is actually the stack we were using also before we got investment from them. So just a disclaimer there. So in terms of the requirements for us, as we deploy in our customers' compute environments so that their data is never shared outside their systems, this means that we need to deploy across a whole range of infrastructure. So we need to deploy on all the big cloud players like AWS and GCP, for example, and Azure, of course. And also a lot of like on-prem installations, also like, a Windows server or something like that. And our system also needs to be highly reliable because it's running in customer compute environments, which means, it's much harder to debug when something goes wrong because we can't jump in and get access to the system. And our customer base ranges anywhere from startups all the way to some of the largest companies in North America. So we need to be able to cost efficiently process terabytes of text. Like we have some customers that do billions of API calls every month. So it needs to be fast. And this is a really wide range of parameters to optimize for. So we actually have two different builds of our system. So we deploy it as a Docker container. And we have a CPU build for easy deployment that'll just run anywhere. And then we have a GPU build that we give to the big users when throughput at reasonable cost is a big requirement. Cool. So basically 2 years ago, we were at the MVP stage and it was roughly a Hugging Face BERT model, running on PyTorch using Fast API. And I figured this is good just to frame and ground our benchmarks. This is a very common setup I see today. So this will be kind of like our reference numbers, so to say. So as you can see on CPU, we can do about a bit less than 10 inferences a second, and the GPU does a little bit less than 100, which gets the job done. But as you'll see, there's a lot of performance to unlock there. So the first step in our deployment journey / pipeline is converting our models outside of PyTorch. For use outside of PyTorch. So the best solution for this, without doubt, in my opinion, is the ONNX format. So that's the Open Neural Network Exchange. And it's a nice platform-independent model. It's open. It is a graph-based approach. So it's kind of like TensorFlow 1, as opposed to like the dynamic computation graphs that PyTorch has popularized. So there's a lot of optimizations that it unlocks. And this format has great support in both PyTorch and Hugging Face. It's the default way to serve models into production. And like 90% of the time, you can get away using the transformers command line, and then it's just a single command line to export a model to ONNX. So it can be really quite simple. Once we've got our models in the ONNX format, that then allows us opens the door to using different specialized inference packages. So basically, PyTorch is built for neural network training. It is not designed to do high performance inference. And whilst this might sound the same because you're just performing the forward pass of the neural network, there's under the hood, these things are actually quite different because, you have to, on PyTorch, you're typically doing batching, and you're also typically, you need to pass the gradients back. So you need to keep all the activations in order to do backprop. And that's not a requirement whilst you're serving. So it's important to know, while they might conceptually be the same, under the hood, these libraries are actually quite different due to the different optimization points. We looked at 3 different solutions, and without doubt, the ONNX runtime library is by far the best for transformers, in our opinion. It performed the best. It has had a load of optimizations specifically for transformers. So a whole bunch of fused high performance operators and stuff like that for things like the GELU activation and the attention mechanism. And we found it to be highly reliable. It has good integration with Hugging Face. There's been a lot of testing done on it. yeah, in my opinion, the toughest thing with doing deployment of neural networks is just like how many just strange, weird bugs do you run into? Because these packages are typically at a much lower level of maturity than training packages like TensorFlow or especially PyTorch these days. So that for me, at least personally, is a very big point. And we found that, Onyx Runtime was really easy to use. We also had a look at TensorFlow Lite, which of course is led by Google. And we found that although it has good x86 performance these days through the XNNPAC backend, there weren't really any optimizations for transformers when we had a look. And it would also involve relying on TensorFlow when we're doing all our development these days in PyTorch. And finally, we also had a look at OpenVINO, which is a serving package made by Intel. But we found it just couldn't match Onyx Runtime in terms of performance. And it really wasn't that easy to use. And I even needed to make some adjustments to the source code in order to get our models to convert properly. So that we definitely preferred Onyx Runtime in that regard. And it's also worth noting that the quantization support and accuracy thereof, so the quality of the operators they've implemented are actually better in Onyx Runtime. That was quite surprising, actually, but another plus for Onyx Runtime. And yeah, like using Onyx Runtime can really be quite simple. So this is a example that I got off the Hugging Face website. So you can see it can really just be a couple of lines to use Onyx Runtime. You just feed it a couple of NumPy inputs, and it's basically a drop-in replacement. So it's really quite simple when it comes down to it. And basically that's our CPU build of our software. So all we've done is we're still using Fast API for serving. And we've basically just taken our PyTorch and put in Onyx Runtime. And this solution works really, really well. So the Onyx Runtime library weighs in at 4.5 megabytes for CPU. And yeah, that results in a really small container. So our Docker container with 3 different models weighs in at a bit over 700 megabytes with all the runtime and all the bits and pieces needed to deploy it. And it runs everywhere. So it runs on any x86 CPU, which is basically any Intel or AMD CPU. And it even runs on the new Intel Macs with their Rosetta 2 x86 emulation. And the beautiful thing about deploying on CPUs as well is that we don't need to do batching to achieve high levels of performance. So it's really a very simple solution that performs, when it comes down to it, quite well. And Onyx Runtime, like you can see from the benchmark here, is a bit over 3 times faster than just using PyTorch. And this difference increases even further if you use dynamic quantization on some of the latest Intel CPUs, which feature the AVX512 VINI instructions. So that's dedicated neural network instructions in the new Intel CPUs. I'll come back to that a bit later. Pardon me. Right, so that's our CPU build. But as I mentioned previously, for the really big use cases, there's just no getting around using GPUs. As I guess everyone's aware, they're really by far the best in terms of sheer throughput. So, but the thing is, to unlock the performance of GPUs, we really need to do batching, which is a problem because our requests are coming in one by one. So for this, we found it's best to use a model serving package, which will, they do a bunch of things, but I guess in my opinion, the main thing is that they're batching all of these requests on the back end and doing batch inference, and then, so you can feed requests in individually and they'll be processed as a batch internally. As you can see, we tried a number of different packages. So NVIDIA's Trident, TorchServe, which is led by Amazon and I guess Facebook. And we also had a quick look at BentoML and Selden. But by far the best was Trident. Onyx Runtime is really great, but I was really taken aback as to just how much better Triton was than everything else out there. It is really, like, I don't know what they're doing inside, but it's a piece of magic. We found it's over 4 times faster than torch serve for our application. So it's really, really fast. And also the GPU memory utilization, especially when you're using multiple workers, which you would, it really uses a fraction of the memory. So the GPU memory utilization, which is of course very important when we're serving massive networks like transformers, that's really important as well. And we found it to be highly reliable. It previously used to be known as the TensorRT inference server. And yeah, it's been around since 2018, which is basically forever in MLOps land. And when it comes down to it, it looks a bit scary up front. And maybe the documentation could be a bit better and there could be a few more tutorials, but it's actually quite easy to use. Torch serve, yeah, also on the face of it, it's easy to use, but by the time, in terms of getting performance up and really squeezing it into our system, we actually found that it was not so trivial. Basically because Triton works so well, we didn't really look much further. So there's BentoML that allows you to easily package models up into a Docker container, but yeah, at that stage we were just like, nothing's going to be better than Triton. And there's also Selden. I think they're also here at this conference, and basically they're an end-to-end turnkey model deployment setup. So for us, that's a non-starter because we don't deploy in our own cloud. But if you do, that might be worth having a look at. Cool. So in terms of benchmarks, putting it all together, you could see that previously, just with Fast API and PyTorch, we were a bit less than 100 requests a second. Triton running together with Onyx runtime, and there's a couple of maybe 1 or 2 more improvements, like 16-bit quantization there. We're able to reach over 1,000 requests a second. So we've increased throughput on the GPU by 11.5 times, while still maintaining basically the same latency. Yeah, to be honest, we could squeeze that latency down a little bit further and still have basically the same level of performance. Yeah, this is really impressive. And I want to take a second here to just highlight how much extra performance you can unlock while still maintaining the same level of latency. So I guess what it really comes down to is cost and relative cost. So yeah, we've done some benchmarks on these particular benchmarks are on the G4DN instances from AWS. So they're the inference GPUs, like the low cost ones. And as you can see, going down to Onyx, Triton and Onyx runtime drastically reduces the cost. And it's also worth noting that, CPUs they are slower, but it's not 50 or 100 times. You can see that in terms of relative cost, it's not actually too far away from the GPU itself, unoptimized. So for smaller deployments where we're not doing terabytes of data, it's actually, it's actually really not that bad. So putting it all together, this is how our toolchain looks like. So basically, we develop our models in PyTorch, and then we convert them to the Onyx format, which is our interchangeable format, which we use everywhere. We then apply either CPU or GPU optimizations. And the CPU container is basically just Fast API with Onyx runtime. So we've basically just taken PyTorch out and put Onyx runtime in. And for the GPU container, we actually run Triton internally and then make post requests from our Fast API workers to the Triton inference server. So that also decouples things nicely. And that gives us the benchmark numbers I just presented. Cool. So that's basically it. That was all very high level. But yeah, I guess it's in terms of closing remarks, it's now 2021 and the Onyx ecosystem is mature and easy to use. So TensorFlow and TensorFlow serving are no longer the only games in town. And transformer model optimization really does matter. And, you can, without too much work, you should be able to unlock a 10x cost reduction in your transformer serving. And basically our recommendation and the best libraries we found were Onyx Runtime for the inference backend and NVIDIA Trident for the GPU model serving. Of course, it's going to be different for different people, but I feel this is still a pretty good way of doing things because it still all boils down to a Docker container, which then basically, at least the CPU container runs like any other. So, your DevOps team will be they won't be familiar with how it works internally, but they know how to deploy containers. And yeah, GPU deployment on clouds is definitely more complicated, pardon me, but not too much more complicated these days. Great. And on that note, I want to say thank you. And that's my talk. Thanks very much for having me.
Thank you so much for the amazing, interesting talk. Really appreciate all the insights that you've shared. Everyone who was listening, if you have more questions, please put them on the chat. And then the first question we have for you, Pieter, is, have you performed any comparison or experiments with TensorFlow and TF serving for model serving?
Great question. Not specifically TensorFlow, but yeah, we did compare against TensorFlow Lite. I guess my background is more embedded, so that's definitely the package I'm more familiar with. And yeah, I guess it's all like trying to fit all the different bits and pieces together. So yeah, from a model development point of view, like PyTorch is, I think it's safe to say, really overtaken TensorFlow in terms of the package everyone is using, and especially for transformers. So yeah, it's kind of, it would be harder for us to go from PyTorch to TensorFlow and then deploy it that way, as opposed to going through Onyx, if that makes sense. So that like connection is easier. And yeah, just being able to use Onyx runtime, being able to actually see the graphs and deploy them. Yeah, I got to say, I'm much more a person who likes maybe lower level tools and then to put the bits together myself, which on the face of it can be a bit more complicated. But really what I find takes time with deploying neural networks is just like, if it works the way the blog articles and the demos and whatnot and the documentation say, sure, it takes next to no time. Like, what really takes the time is how many bugs do you run into? And these days it's pretty good, but it really did not used to be that way. So yeah, especially also with the reliability thing and just Onyx runtime and Onyx being as popular as they are today, together with PyTorch, we just felt it was the safest solution. Also, TensorFlow Lite really didn't have many transformer optimizations. So yeah, at that point, we also felt it probably wasn't really worth having a look at TensorFlow serving. But great question.
And so follow-up question, and it ties back with your answer really well, is what exactly are the transformer transformer inference optimization in Onyx runtime?
Great question. If I had a bit more time, there's a really wonderful tool called Netron, and that allows you to visualize Onyx models. And what you can actually do is put an Onyx model before and after optimization through it, and that'll show you what it does. But I guess at a high level, what it does is it fuses a lot of these operators together. So, for example, GLU has a whole bunch of different operations, and it's actually better to perform that in one kernel for caching and stuff like that than it is to do it as separate operations. And it's the same thing for things like attention. Like, Yeah, like the amount of optimization that goes into neural network libraries these days is really quite incredible. Like when you're using PyTorch with CUDA, like CUDNN or something, that could be 15 or 20 different like hand-coded or optimized implementations that it's actually picking from under the hood. So there's just a huge amount of like hand-coded, like assembly level programming going on. So they're programming directly in the AVX2, AVX512 and AVX512 VINI instructions. So it's really quite impressive, actually, all the stuff that goes under the hood. And that also ties back to Onyx Runtime. It can do training, but it's really built for inference. Whereas PyTorch, especially CPU side, that's really just not what it's built or designed or optimized for. It's a great piece of software, but there's not one silver bullet that does everything.
Yeah. Thank you. So a follow-up question from different people, but that's very interesting how all it comes together. How smooth is the PyTorch to Onyx export? Did you face any challenges?
Yeah, great question. And that definitely ties back to when it works, it's great, but how many bugs do you encounter along the way is the time it takes. Yeah, as I said, it works about 90% of the time with the Onyx tool. One of the problems, I think, one of the things that makes Hugging Face tough is that they have a whole bunch of different models and then a whole bunch of different use cases. So they actually have hundreds of combinations that could be going through that particular tool. So we actually don't use it. We actually do a bunch of like lower level stuff that also gives us more control, and also like on top of the stuff I've presented here today, we do a whole bunch of additional optimizations that also ties into. But it's still all built on top of some pretty simple operators, so it all works on top of the PyTorch Onyx export command, which works really well today. But great question.
Thank you. And then last question I have here, did you get a chance to look at Apache TVM? tvm.apache.org?
Yeah, great question. I have to say I'm not too familiar with TVM. I kind of don't follow that one too closely. Yeah, really, when it comes down to it, like reliability is just such a massive thing for us, and like Onyx Runtime is pretty reliable. There's a lot of work that's gone to developing it, and it's really built especially for transformers. And really that reliability argument is just key for us, because we're a startup. We only get like one, maybe two shots with a customer, and then we're out, right? And yeah, I can happily say that we've had 0 bugs in production right from the very beginning. Yeah, and that's really I think helped us, and really helped us close a lot of deals that, hey, we're a startup, but this is not a MVP level product. This is something ready for inference. But great question.
Thank you so much. And they said makes sense. Thank you. Awesome. Great talk, great questions, and great answers. Thank you so much. Any other questions anyone wants to add, like last minute question?
One other thing I might add as well, actually, I put up some further links. So one, of course, is our blog, where I sometimes do write about stuff relating to deployment. But there's also this blog article I just noticed on Towards Data Science. And this is a really great article and almost exactly matches our deployment setup. So they're also, using Onyx Runtime together with Trident to deliver under sub 1 millisecond latency model serving. So that's a different optimization point for us. We're looking more how much throughput we can get at a reasonable level of latency, which is about 50 milliseconds for us. So that is different, but they actually managed to, I think, match, if not beat, Hugging Face's new model deployment solution that's like built for enterprise and costs a whole bunch of money. So very, very impressive article that I highly recommend you everyone check out in case you're you want to walk down this path, I guess.
Thank you. Thank you for sharing that. That's very helpful, and really appreciate the time. Great presentation and great answers to great questions. Really appreciate your time, Pieter, and our audience. With that, we will wrap this session up. And thank you so much again for joining us. And thank you so much, Pieter, for the presentation and great insights.
Thank you. And if anyone wants some advice on model serving, I definitely like talking about it a lot. So feel free to shoot me an email if you would like. And thanks very much for having me. I really appreciate the opportunity.
Awesome. Thank you so much, everyone. Have a great rest of the day. Thank you, Pieter.